Hello everyone, this is Minyu Liu. Welcome to this session. My talk today is about recent advances in semantic image synthesis. The semantic image synthesis problem is about converting something human can describe to an image. Let's say we have a generator. That can convert human descriptions in a sentence to image. The example here is an armchair in the shape of an avocado, and the generator can generate images corresponding to this language description. The images here, they capture the idea of chair, something that people can sit on top of it, and also have the appearance of avocado. And I think many of you have seen these images. It's from the OpenAI DALL-E model. It is based on transformer trained on a huge quantity of text image pairs. Another popular form of semantic image synthesis is to convert segmentation mask to images. Segmentation maps is an image where each pixel indicates the semantic class of the object. For example, the pixel can be a tree pixel because it's from the tree region in the image. It's a cloud pixel, soil pixel, and grass pixel. And this is also something human can draw with some kind of Microsoft Paint-like tool. You can describe an image by paint semantic labels on the canvas. And when use different semantic labels, different semantic images, then you have different output images. And today, the focus will be mostly on this form of semantic image synthesis, converting a semantic segmentation mask to a photorealistic image. Let's talk about training. We often assume input and desired output supervision is available in the training dataset. So we could have a dataset of paired language description of an image, caption and image. Xi is the caption, Yi is the image. We can also have a dataset of input segmentation mask and output target image. So the Xi, Yi correspondence give you the supervision you need to train the network. There are two popular objectives to train a semantic image synthesis model. One is the maximal likelihood learning, and the other is distribution matching. In maximal likelihood learning, we want to maximize the likelihood for each sample to confound the target distribution. So let's say G is our generator. It's convert the input Xi to a fake image G of Xi. And let's say Yi is the ground truth. And let's say we have a way to measure the distance between two samples, between the generated image and the ground truth image. And maximal likelihood learning can often be reformulated as minimizing the distance between the image, the generated image and ground truth image in some sense. And because we want to take care of the whole data set, so there's a summation here. So intuitively, you can think that you have a distribution and you have different samples. Each star is a real sample. So we want a generator G that can convert the inputs to a set point where each will be close. Each reconstructed image, synthesized image will be close to the ground truth image. So every ground truth image should be covered somehow. Distribution matching is different. It's different in the sense that it cares more in the population level, right? You want to minimize the distance between two distributions. Let's say we have some kind of way to measure the distance between two distributions, right? It can be the Jason-Sheldon divergence, chi-square distance, whatever measures you know, right? And now instead of focusing on sample to sample matching, like in the maximum likelihood, distribution matching focus on population to population. So then you could let's look at this distribution again, right? You have a distribution. Now you reproduce the distribution with the generator. Now you don't focus on point matching, right? You just have a set of samples that distribute similarly to the ground truth, and that is good enough. Yeah, so this recover distribution. But if we only focus on distribution matching, it could lead to the mode dropping problem. Sometimes some ground truth sample, some ground truth mode is not well covered. And I think this is pretty common in existing frameworks, especially for generative adversarial networks. Right, you know that GAN is based on minimizing the Jason-Sheldon divergence or Wasserstein distance. There's a couple of other variants, but they are focusing on minimizing the distribution distance. And there are other models such as flow-based model or VAE. They operate more in the maximum likelihood space. All right. And in today's talk, in the following work, you will see people actually use both to solve this semantic image synthesis problem. Let's start with the seminar work, the image-to-image translation with conditional adversarial network by Isola et al. This is the PIX paper. So they use a GAN framework, so they have a generator and discriminator. And what they do is they give an input segmentation mask. They use a UNet to generate an output image. They want the output image to be similar to the ground truth in L1 sense. They use a discriminator to check if the output image has distribution similar to the ground truth image. They operate in the conditional setting. They assume that they know the segmentation mask. In this setting, it's a right assumption. And what they do is they concatenate the output image and the segmentation mask and feed into a patch discriminator. So instead of produce 0, 1 for the whole image, they produce an array of 0, 1 for the whole image. And this is beneficial because you may not have enough samples to cover the to learn a good discriminator, but you have many patches from the images. So in some sense, using the patch discriminator, you focus on the local textures if they are good enough. And you can do that because you have these L1 loads to measure the global the structure of the image, where the mountains, rocks, ocean are kind of correspond to the inputs. All right, so this is the P2P work. All right. Later, let's work called P2P-HD. They input the P2P framework to achieve high-resolution synthesis. And what they do is they replace the UNet with ResNet and replace the L1 loads with perceptual loads, the VGG network-based perceptual loads, and they push a little bit on the patch gain and use this multi-resolution, so they have a multiple discriminator operate at different resolution, and this leads to improved performance. Now let's talk about the paper semantic image synthesis with spatially adaptive normalization, Spade, the Spade paper. So the Spade paper make a couple improvements over the P2P-HD paper, the previous paper. First, it's introduced a modulation layer called spatially adaptive demodulation. So the segmentation mask is no longer inputted from the head of the network. It's now input to different places in the network through this spatially adaptive normalization. I will explain why such design is made. And the head is now optionally configured taking a random noise input, and this random noise combined with the VAE training, it can be used to encode the style of an image. And now sample different Z using the same segmentation mask, you can have different output image. And the Spade also use spectral norm. We'll explain what spectral norm is in the later slide. So okay, so there are many different ways to implement the spatially adaptive concept, and the particular implementation in the paper is called Spade. And later we'll see paper use different implementation. So the Spade design is motivated by this the issue with a batch node when it's applied, when the batch node is applied for semantic image synthesis. The operation of batch node is very simple. You have the activation of the channel at a particular layer. You have n sample and different y-x location. You subtract the activation value by the mean and divided by the deviation, then you have normalized activation. And then you use a learned constant gamma and learn the bias beta to shift the distribution to a desired location. This is beneficial for training very deep network. However, it's cause problem when applied to semantic image synthesis. We have two segmentation masks. One is purely sky, the other is purely glass, and they have different semantic labels, but uniform maps. Now, apply convolution, you get the same. You get uniform maps output again because input is uniform. Then apply batch node. The mean is subtracted. So the only information left is this beta value, and the network has no way to tell whether the input is sky or glass, and this causes issues. So with the Spade, we fix the issue. So P2P-HD use batch node. When you input purely sky, it gives you great outputs similar to input glass. But with Spade, you have maps corresponding to the input. You have the sky texture, glass texture. And how is the Spade is implemented? It's very simple. It simply replaces the learned gamma and beta constants with a neural network that operates on the input segmentation mask. So you can imagine a fully convolutional network take a segmentation mask input, produce the gamma maps per each pixel has a different value, and similarly the beta map, each pixel have different value. So while this normalization step kill the semantic information in the inputs, the information is resupplied through this demodulation step in the batch norm. So what is spectral normalization? It's a technique introduced by Miyato et al. Let's say we have a k-layer network. We ignore the nonlinearities and other operation, only keep the weight, the convolution or fully connected layer, the weights in the layer. W1, W2, the weights for different layer. In the paper, they suggest that we divide the weight by their spatial norm, the largest eigenvalue. And this way, we have each layer always has a spatial norm 1. So this network is each layer is more restrictive because spatial norm has always to be 1. I mean, if you don't apply the normalization, spatial norm can be anything. So using spatial norm limits the expressiveness of the network, but helps stabilize the training. This technique was found useful for training semantic image synthesis models. Okay, now let's talk about another recent paper, learning to predict layout to image condition convolutions for semantic image synthesis. This paper adapt a couple of things from the previous Spade paper. They still use a spatial adaptive operation, but instead of demodulation, they predict the convolution kernel. But more interestingly is that they replaced the patch gain with this feature pyramid projection discriminator. Notice that the input to the discriminator is no longer the concatenation of segmentation mask and the output image. It's just take the output images and produce some feature, and the feature is inner product with the embedding of the segmentation mask per pixel, and they are added to produce the output. And this help improve the performance. And there's all the previous work more or less rely on this perceptual loss to stabilize the training. In this recent paper, you only need adversarial supervision for semantic image synthesis. They found that they can remove this perceptual loss if they use UNet as a discriminator. And these UNets, in addition to produce real and fake, but also learn to label the images. So this is solving two tasks at the same time: semantic labeling and adversarial training. And they use a technique called label mix to help train the UNets. For more detail, please refer to the paper. Okay, Temi transformers for high-resolution image synthesis. This paper is very different to the earlier papers on this topic. It uses a vector quantization model. So it's first trained image reconstruction model, but the latent code are some kind of discretized token. So they use a vector quantization encoder to discretize each patch, and they use a vector quantization decoder to convert each token to an image patch to reconstruct the image. When it's applied to the semantic image synthesis task, they also train a vector quantization encoder for the segmentation mask, and also learn to decode it to the output segmentation mask. Now you have two vector quantization model. Finally, they train a transformer to map the segmentation tokens to image token to generate the output image. And this model has been achieved some impressive results recently. Okay, so that is all for today. I would like to thank for your time, and welcome to join the Q&A sessions for more discussions.